infinity element can be written as, in this form, x to a power. And what's the value of p here? 1, right. All right. And then our quadratic function has the power of 2. And then do we have cubic on our toolkit function? Yep. So read right down your toolkit function, and we have 3 for the value of p. And what do we have next in our toolkit function? If we look right down the line. Nobody has packet 1 available that can turn it to 6 and 7, or you want your classmates to do your work for you? Yes, Peter, that's what you said, yeah? Okay. What's absolute value? Can absolute value be written as something to a power? No, it cannot. Nope. It's a piecewise function. So you need 2 equations to represent that. It's not, you cannot represent it as one singular function as x to a power. Okay, then what's next, Benny? Square root. Right, so often we look at square root like this, but how do we write it with an exponent? 1/2, so what's the value of p? 1/2, perfect. What's next in the toolkit function? Cube root, so we know if the square root works, the cube root's going to work as well. Okay, what's next on your toolkit function? Reciprocal function, right? So the reciprocal function looks like this. And can I write that as x to a power? -1, yep. We have any more? Reciprocal squared, we can write as x to the -2. And then why can't I include exponential? Why can't I include an exponential? I'm telling you, you cannot include an exponential. Why not? The value of p changes. Yeah, I guess we can't even talk about the value of p with an exponential. So that needs to be edited, but it's a good guess. Why can't I include an exponential function? Here's a power function, x to some power, p. What's a regular old generic exponential function look like? You just use them on your test. Give me a baby exponential function. Generic, not with any numbers in it. Okay, that's a little more transformed. How about b to the x? Right? So what's the problem? Yeah, look at where your variable is. Right there. It's not down there. It's not the base. So people often confuse power functions with exponential. And there's a huge difference. Okay, with your power functions, your variable is your base, and you have a power that's constant, whatever the particular function happens to be. Like, look down here. You have a bunch of examples. With your exponential function, your variable is the value of p. So to edit what Nick said, p would be a variable, right? So it's changed, but it would be a variable. It's no longer a constant. All right, now there could be a little bit of a controversy with adding the next one, and I just want to talk to you about it. What's your very first function on there? Constant, and how did they represent it? F of x equals c or a or some letter at the beginning of the alphabet, because if you've never noticed, we use the letters at the beginning to denote constants, right? Like think of ax squared plus bx plus c. A, B, and C are coefficients, right? So we often use the letters at the beginning to represent constant values. If I were to write that so it had an x in it, how could I rewrite this so it had an x to a power and it would still be equal to c? Can't call it cx, and it's a line. What power can be there? 0. Because what's x to the 0? 1. So here you would have 0. But that function, even though technically it's a power function, it doesn't behave in some of the same ways that these other functions do in terms of the long run behavior. We'll talk about that in a minute. All right. So your book now asks this question: what points do the toolkit's functions have in common? And then they give you an answer that I disagree with. They give you this answer: 0, 0, and 1, 1. And I disagree with that. And Irene, I think you pointed out why we can't talk about, was it Irene or Hannah? One of you. Hannah, was it you? Talked about why it couldn't be 0, 0. Yeah. And what's the reason? Right. 0 isn't even in the domain of your reciprocal function and your reciprocal squared function. It's not even part of the domain. It's where your vertical asymptote is. So 0, 0 works for everything except your reciprocal function and your constant, because your constant function has an output that's constant. So it doesn't have 0, 0. So even though your book lists this, I don't agree with that. It doesn't work, does not work for all. What about 1, 1? Does that work for all of them? Except for the constant. Because what's true about a constant function? No matter what you put in for x, your output's whatever that constant is. It's a horizontal line. So again, I have a little bit, you know, I guess I should write to the authors, and maybe I will probably after the end of the semester and talk about this with them or mention it to them. I'll go on their forum or whatever. This is how they learn, right? So 1, 1 is a point for every single power function except doesn't work for the constant function. F of x equals some constant, A, B, C, whatever you want to call it. All right. So that was just to sort of get you thinking powerfully. Well, someone appreciates my humor. That's nice. All right. So let's take a look at your seats. I'm going to give you a couple minutes. Talk about A and B here, and then we'll come back. All right. So let's talk about this quickly, I hope. So could f be a linear function? No. Big no. How do you know? There's not a constant rate of change, right, between the two variables. Even though x is changing by 1, right? Change in x equals 1. The change in y is not constant. It's 3 here, and here the change in y, the difference is 5.485, right? And then it's different. So the rate of change is not constant, so no non-constant rate of change. What about exponential? No, I have one no. What's table 1 say? No. Table 2? No. Why not? The values of 4 and 5. You mean x equals 4 and x equals 5? Okay. They do not change exponentially. Well, that's what we're supposed to figure out. How do we know that this is not changing exponentially? How do you show when something is changing exponentially? When it's constant, we can add or subtract something from one y value to its successor, right? What about when you have an exponential? What do, Peter? Okay, so Peter remembers most of it, right? He said if you divide successive f of x values, so here's a f of x value, this is f of 2, right? And this is f of 3. So if I divide f of 3 by f of 2, this is called a ratio. So if I divide that ratio, let's see what I get. Call it my little wabbit here. Let's see, we got 15.5 88 divided by what? 8.485 is that number, right? We're just going to write here approximately, and I already lost it. See this 1.8, let's go a little further than that. It has to do with the smart notebook, because this used to always stay right on top. And the minute I write now, 837,124, 837,124, okay. So what does that mean? That if I really had this ratio here, I could multiply this f of 2 by that ratio and get f of 3, right? It should have a constant ratio, a constant multiplier, a constant multiple, right? So now you got to check out your next one. If you do f of 4 divided by f of 3, you want to see if you get that same ratio. Well, let's see. I'm going to put that ratio, I'm going to store it in alpha A just so I can compare it. Let's see, f of 4 is 24, and I'm going to divide it by f of 3, which is 15.588. And does not equal that ratio. So this does not have a constant ratio between successive outputs, but there's something looking at you smack dab in the face that should have told you, like, boom, there's no way this is exponential. Hannah, were you about to raise your hand? Yeah. 1, 3, and 4, 24. Why does that tell you they couldn't be? Three is the base. That's right. Well, that's one way. Like, we always know that this is like a really important point on an exponential because it tells you your base. So if your base is 3 and you raise it to the 4th power, you're not going to get 24. But what else? Like, it's like screaming at you, Hunter. Can't go through 0, 0, folks, right? What point does all of our parent exponentials have, or our parent exponential? Well, nope. 0, 1. They all go through 0, 1 unless they've been transformed somehow, right? Can an exponential function, when you put 0 in, ever give you a 0? No. It has a horizontal asymptote, right? As x goes to infinity, the limit is 0, but it can never be 0. So right there, that's all you needed to say. No way, Jose, right? There's no way. 0, 0 is not part of an exponential function. All right. Now, the next question was, could this be polynomial? And I decided that took too long to answer, so I removed it. But if for those of you who like thinking about math, sometimes I get people who like thinking about math, you might want to just think about that question. So I'm going to tell you that this data can be modeled by a power function, and it's going to have this form. So let's see what that power function is. So if we're going to define any power function, now notice this is a little bit different than our original definition, because this is what? A transformed power function, right? It has k out here, which is like a scalar. It's a multiplier. So let's take a look. We got to find the value of k, and we've got to find the value of p. So thank goodness we did all that exponential work, and we know how to find functions based on 2 points, and we know how to solve exponential equations, because we got to eventually solve for p, which means we got to get it out of the air. So we have all the skills right now. I don't know why they have chapter 3 before 4. It doesn't make sense to me. But anyway, so we go back to our table here. Let's pick 2 points. Why not pick some nice easy points, right? So let's pick 1 and 3. And 4 and 24, but it will work for any of these points, okay? So let's start this. We know our job is to find the value of k, so we've got to figure out our value for k and our value for p. So we've got to find k and p. So we use 2 points. Let's go over here now. So let's use 2 points that we know lie on this power function. We know the point 1, 3 is on that power function. So what does that tell us? F of 1, when I plug 1 into my function, outputs 3. So let's see what f of 1 would look like. It would look like this. k times 1 to the p, because I replace x with 1. So I know this, 3 equals k times 1, because 1 to any power is 1, right? So, boo, that's a great point to have that Jackson picked out. We already know what the value of k is. It is 3. So I can come up here, f of x, and I can put 3 in for k. Well, I'm halfway home now, right? Now I just have to find the value for p. So we found the value of k. Let's use our other point that we know any of the other points, but I like to try to work with, what was it, 424? Okay, thank you. All right. So now we know that when I plug in 4 for x, my output is 24. So let's plug 4 in for x. I know k is 3, x is 4, and now I've got to solve for p. So let's write this equation without, we'll just remove this. We'll move that aside, and we'll say 24 equals 3 times 4 to the p. And we don't have to freak out anymore because we know how to solve these equations. We divide both sides by 3, and we get 8 equals 4 to the p. So how do I solve for p? Logs. Common log or natural log, it's up to you. Natural log of 8 equals the natural log of 4 to the p. The p comes down in front with our log property. And now I solve this equation, which now looks just like a baby linear equation. Some number times p equals another number. I divide both sides by log of 4. Oops. Oh, I switched my logs on. Okay, Linda. Sometimes, you can kind of lull yourself into doing stuff like this when you're so used to doing it. All right, natural log of 4. So p equals the natural log of 8 over the natural log of 4. So let's see what that is. Now, if it was some yucky number, you would actually put that value in for p. Put in the quotient of both of those logs. It's okay. It doesn't always have to be a nice number. Let's see. I think I made this so it came out to be a nice number. Yeah, it's pretty nice. Okay. So let's take a look. But it isn't always nice. Natural log of 8 divided by the natural log of 4. Oops. Is 1.5, or 3/2. So p is equal to 3/2. 3/2 or 1.5, however, whatever you prefer. So our power function would have this form. F of x equals 3 times x to the 3/2 power, or you could write it as 3 times x to the 1.5. Right? Everybody all set with that? Kosher? Yes? Questions? Okay, let's take a look at, we sort of have already done this with our preview exercises, but this will just help us get used to the idea a little more. A transform power function is any function that has this format, k times x to the p. Which of these functions are transform power functions? How would we write them in the form of f of x equals k times x to the p? State the values for k and p. So since we've just done a bunch of the preview exercises, what I'd like you to do at your seats with your table is write the values for k equals and p equals. And we have 5 problems here and 5 tables. Isn't that special? So I'm going to assign table numbers, and once you all agree at your table, then for all of them, then one person can come up and record. Any questions after you've gone through what every table's put up there? Any questions about anything? I do. I'm in absolute total agreement with everybody. Yay. All right. So we've already talked about this first paragraph about how easy it is initially when you're looking at power functions to confuse them with your exponential functions. And remember, your exponential function, your variable is the power versus your base, which is what it is in your power function. Okay. So in the power function, k serves as a scaling factor, and all you have to really do is think of a straight line. Think of y equals x, right? Right through the origin. And when k becomes a 2, 3, 4, 5, your slope increases, right? And it's moving a point, say, let's take a look at GeoGebra really quick here. Come on, hurry up. Oh, I hit the wrong box. That doesn't help. It's that one. Okay, so let's take a look at I'm not going to be able to do it on here because I have something else set up for you. So let me call up another one. Well, let's start now. All right, call it. It's so easy to do on GeoGebra. I just don't want to destroy what I've got here. Let's I'll just do it old-fashioned way, which is here's a straight line, y equals x. If I drew a line down through the point 1, 1, and now I change the scalar out here from 1 to, say, 4x, we know that this thing will be steeper. And you can see that for the same value of 1, you have 4. So that scalar acts as moving or increasing that if k is a positive number, or decreasing it if k is a fraction between 0 and 1, right? Decreasing the steepness. K and m for this function are equivalent, yes, for your linear function, for your identity function. Yep. Yep. So let's see. Let's go back here. So when we say this in general, we say it moves the values of x to the p up or down, but don't think about shifting. It's moving it because the rate of change is increasing or decreasing. Okay. I'm going to leave this next one for later. So let's take a look at different power functions. Now, this is the really nice thing about power functions. There aren't that many different types of graphs that you've got to think about. And most of these graphs, you already have a good visual in your mind because you did all that transformation work back in 107. And you just did little mini graphs for your toolkit functions. So as an example, you're very familiar with the graph of a parabola, whether it's x squared or some number out here multiplying x squared. All right. So the graphs of kx to the 4th and kx to the 6th and kx to the 8th are all basically the same as your parabola. So let's take a look at these, and that's what I've set up here for GeoGebra. GeoGebra is great for doing this. So notice here, I've got my green function f of x equals x squared. We'll start with x squared. I've got k equal to 1 in all of these. So let's take a look. There's your basic parabola. Now, if we have an even power, which is what this first thing is, right? Isn't that what it says? What does it say? P is what? Odd? All right. And let's go to odd. I've taken care of that too. Is odd. So there's your x cubed. Okay? It's always increasing from negative infinity to positive infinity. Every single step of the way, your function value, the output values are increasing. To the left of 0, it is concave down. To the right of 0, it is concave up. And when you get to calculus, you'll learn a special name for that point right there where your concavity changes. Some of you may already know it. Okay, so we're saying that from this point on, as long as you know the shape of your basic x cubed, you know the basic shape of x to the 5th, x to the 7th, x to the 9th. Let's look with this slider. Let's see what happens. There's the 5th, there's the 7th, and there's the ninth. So even though it looks like it's a horizontal line, we know it isn't. It's ever increasing minutely, and you can see that beautifully on GeoGebra by making the increments of y smaller and smaller and smaller, so it doesn't, I guess I should come down so it's not ninth. But, and then you can come this way. So you can see that it isn't horizontal. You can keep going. Look, I'm way, way down now to the -8, but it is always increasing. So it's just basically this shape. Woo! Let me come back to my original scale. With the sound effects. Okay, so it looks like it's a horizontal line there, but it's just that the width of this line and our axes is just not enough space between them, you know, with the creation of the graphic. Okay, so you'd say, what about x equals 1? Well, x equals 1 is a bit of an outlier here. It has the same idea, but it doesn't have the little wiggle in it, right? It's always increasing over the whole domain, okay? It just doesn't have the little wiggle that the cube and the fifth and the seventh and the ninth have. Okay. So let's go now to our even functions, oops, which is your next little thing to look at. Oh, I asked you about end behavior. So what happens with these positive odd functions as x goes to positive infinity? What does the value of the function approach? Positive infinity. It grows without bound. And as x goes to negative infinity, negative infinity. So you can fill that in right below the picture you have. All right, so now let's move over to the even, positive even. There's our basic parabola, and all that happens as we increase by 2 to the next even is we get flatter and flatter. And okay, flatter and flatter. Always increasing. You can see the end behavior here. As x approaches positive infinity and negative infinity, our output values approach positive infinity. They grow without bound. Now, if you were using limit notation, I noticed your limit notation was very weak on the test. So let's write this with limit notation. You would say the limit as x goes to positive infinity of f of x, because that's your output, right, equals infinity. Doesn't equal a number. Doesn't have a limit. Doesn't exist. All right. So you can spend more time thinking about that when you get to calculus. Like, do you write infinity there, or do you say does not exist? Right. Now, what else? What's the next graphic you have to draw there? Change your page. Negative what? Negative odd. Okay, well, here I have my odd. G of x is my odd. And here's my slider. So we got to go negative odd. There's 1. So hopefully my next... Ooh, there's a negative odd. What kind of picture is that? Your reciprocal function, right? This is f of x equals 1 over x, or x to the negative 1. As x goes to positive infinity, what's happening to your values? What are they approaching? 0, right? So if we were writing this in limit notation, we would say the limit as x goes to infinity of f of x equals 0. And what about over here? The limit as x goes to negative infinity of f of x is also 0. Which are horizontal asymptotes. There's a name for this kind of function. Does anybody know, other than reciprocal, the shape, what we call these? Do you ever have conic sections in high school? We'll have them at the end of the semester. It's called a hyperbola. All right, what's your next thing? So what do you think is going to happen to this function as I see how it's getting? it's just flatter and flatter. Getting that horizontal idea, right? Looks like it's getting almost horizontal, but it isn't. All right, so what's your next one on there? Negative even, so that's up here, and we're going to do negative even. So here we go, -2, our reciprocal function squared. -4, again, it just gets flatter towards the horizontal asymptote, right? All right. And you can play around with these on your own. Let's do the next one is what? 1 over p, where p is even, right? Yeah, that's your, here's 1/2. This is your square root function. So what do you think is going to happen with 1/4, 1/6? Just see if you can, in your mind, think about that for a second. What's going to happen to this picture? And then we'll do the little, there we go. See? All the same shape. So kind of once you have the basic shape, you're good from there. Now this is negative with an odd number. There's your cubic, right? That's your cubic function. It almost looks like a vertical line, but we know it isn't because it's a function. Okay. And then when we have negative, that's what it looks like. Okay. It just gives you an idea of playing with the power functions. All right. So let's take a look at the next part of our section here. We've done all that. So 5, I think this is very similar to how we started class off with finding the power functions formula. So I'm going to put this as lesson activity number 1. You can start your lesson activity with this one. Okay, because we just did one like this, no sense in redoing it. All right, so I'm going to breeze through this section because this should be all familiar to you. Polynomials, functions. And I love this definition. Now we can use this in 108. It's easier to explain. It's the sum, and remember, every time you say sum, you could also have a difference. It's the sum of a bunch of power functions, all with non-negative exponents, because your power functions have 0, 1, 2, 3, or a half, or a third, right? But polynomials are power functions that have just non-negative integers, 0, 1, 2, 3, 4. So they're really nice to graph, and their domain is always all real numbers. And these little coefficients out front match. Notice the subscript matches the power for each term. Those are called your coefficients. And a sub n is the leading coefficient. It's the leader. So whatever your highest exponent is, if it was a cubic, that would have a sub 3 as its designation, as its address. So this is the leading coefficient. Yeah, and this is all review from 107. You could probably fill this out on your own. So what do we call the leader of the pack right here? What do we call that one? Leading term, right. And your leading term here is going to dominate when we look at end behavior. It doesn't really matter what happens after that leading term when x goes towards positive or negative infinity. The blank is n, the highest exponent. What can I fill in there? What word? Degree. The degree of your polynomial is your highest exponent, or the value of n. Values of x for which f of x equals 0 are called zeros, right? They're called zeros. They're the value of x that makes your function 0. Zeros, and there's also another name for it that your book also brings up. It's called the root of your function. That's just another name. Zeros. You can spell 0 ES as well. I think it's both acceptable. And there are how many of them? If you have degree n, if you have a polynomial function of degree n, how many of these zeros can you have? No? Same amount, n. Now, if we're talking about any type of number, real, complex, imaginary, it's n. That's why we write n. If we were just talking about real numbers, we would say at most n. But we have exactly n roots, always, or exactly n zeros. Places where the graph changes from increasing to decreasing or vice versa are called the what? They're turning points. Yep. Another word you might have learned along the way are maximums and minimums, right? Relative maximums and minimums, absolute maximums and minimums, local maximums and minimums. But to cover all of them, we use the term extrema, which is a plural. With the A at the end, it's plural. Individually, they're extremum, M-U-M. So here's a couple of polynomials here. What's the most number of turning points we can have? Now's your answer, Jackson. N minus 1. You always have one less than the degree. At most. Doesn't mean you always have that many, but at most, you have n minus 1 of them. Okay. All right. So here I have your x squared in black, your x cubed in orange, and your x to the 4th in purple. And if we're interested in looking at the long run behavior, that's what happens to the value of these functions as x goes towards positive and negative infinity. Let's take a look at this function right here, g of x. It's a 5th degree polynomial, and what I'm saying is that this first leading term, this power function, think now power function to the 5th. Well, here was my cubic, and now my 5th power looks a lot like that. And now I'm multiplying it by 4, so it's getting bigger faster than x to the rate of change is growing quicker. So think about x being large. I only picked 100, but that's pretty big for when you're raising to the 5th power. So if I just evaluated this term at 100, then you have, what is that? Thousands, 40 billion, right? So just this term alone, the first term would be 40 billion. If I now evaluated all the rest of these terms at 100, here it is, right there. All the rest of them would only equal negative 969,000. Hey, when you have 40 billion, you don't even care about someone taking away 969,000 from you, right? And look what the end result is. 39,999,000,000, blah, 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 and some change. So it's very close to 40 billion. So the moral of the story is, and that's what, does anybody know what this little thing stands for? Therefore. That's how we write therefore in mathematics. It looks like bowling pins, right? Therefore, for large values of x, the leading term leads the way. It totally dominates the rest of your polynomial as x moves towards positive and negative infinity, and it determines the long-run behavior of your graph. So you never have to worry about all the stuff after it. You just have to picture that. And you know your odd degrees always has an arm up and an arm down, one of them. If k is positive, your right arm's up. If k is negative, your right arm's down. Evens, arms are always up or down. Okay. So once you have the general idea of just that leading term, you know the end behavior for your whole polynomial. And here I've written it out for you. All right. So let's do this really quickly. Spent too much time on the toolkit functions. What's the degree of this polynomial? Well, I've given you the function right here. So what's its degree? 3. It's the highest power you see. How many real zeros or roots does f have? Well, when is my function output 0? I cross the x-axis 3 times. So I have 3 real zeros in this case. How many local maximum and minimum do I have? Well, let's see. I've got a relative maximum or local maximum right there. And I've got a relative or a local minimum there. Or I have a local extremum in each case, however you want it. Or I have a turning point. I have 2 of them. And notice 2 is equal to 3 minus 1. Describe the long-term behavior. Just think about that right there, the x cubed. Doesn't matter about all these little squiggles and wiggles. The long end behavior works exactly the way x cubed does. So the limit as x goes to infinity, well, let's just forget the limit for now. I don't want to get you involved with that. Let's just say as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to negative infinity. And here's what we've already discussed earlier. I'm so reluctant to do quadratics. I feel like you should have quadratics like out your ears by now, right? So here's a quadratic function in what we call vertex form, or the transform form, because if you start off with x squared, which is vertex at 0, 0, if you go up 2 and to the right 3, you can now write your new quadratic function in this form by just talking about your new vertex. So h and k here are the coordinates of the vertex of this parabola. And we know anything like that is a happy parabola and anything like that is a sad parabola. Again, this is all, you've had this a zillion times. The only thing you have to really know how to do is to be able to work your way from one form of a quadratic function into another form of a quadratic function. So this form down here is what you're used to seeing, ax squared bx plus c, right? That's usually what you're used to seeing. This is like the what we call the standard form. And up here, because the vertex is staring you right in the face, we call that the vertex form, or as I mentioned, the transform form. Vertex form or transform. So if I was given an equation in this form and I wanted to find its vertex, there is a formula that I use. Does anybody remember how to find the vertex when you have it in this form? It's part of the quadratic formula. Almost. Negative b over 2a, right. That's the x value of your vertex. And to find your y value, you just plug that value of x back into your function and out pops your y value. So if we were to find the vertex of this function right here, the x value of my vertex, or what we call h, is the opposite of negative 6 over 2 times 2, which is 6/4 or 3/2. Now to find the y value of my vertex, I plug in h, the value of h, into my function. So let's see, 2 times 3/2 squared minus 6 times 3/2 plus 7. 2 times 9/4 minus 18/2 plus 7. 18/4. Now I got to change that to fourths, so that's 36/4. And I change that to fourths, it's 28/4. So V is going to be negative 18/4 plus 28/4. Oops, 28. Did I change that to fourths? Yeah, fourths, which is what? 10/4? So your 18, what is it? 10, right? So your vertex is 3/2, comma, 10/4. All right. I did that fast because I want you to have time to spend on your activities. Long demo today. Okay, so your activities are here. And don't forget, there's only 4 of them, but I want you to also add this power function to it. This where we ended off. Where was that? What page? Right here. Add this to your activities, number 5. Okay. Go back where? You mean finding the vertex? You can do that in your sleep. Yeah, you can do it. There it is. If you want to see it, make sure I didn't make any mistakes. I did it so fast. Huh? Did I screw up? Oh, 5/2, yeah, of course. Yep. That's right. All right. I will pass back your exams at the end of the hour.